There is one architectural feature that can make even the hottest day feel much more comfortable. You can see it on old houses in the southern United States. It also appears in the colonial architecture of India. Similar structures have been used for centuries in West Africa, Southeast Asia, and Australia. These regions were separated by thousands of miles. People built with different materials, lived in different climates, and belonged to completely different cultures. They all arrived at almost the same solution. They surrounded their homes with deep, open verandas. Today we think of a veranda as an ordinary place to relax. People place chairs there. They drink coffee. They grow plants. But originally, the veranda was not created simply to decorate a house. The deep veranda was one of the most effective passive cooling systems developed long before air conditioning existed. At first glance, it is simply a roof, several supports, and an open platform. But together, these elements can significantly reduce the heating of walls, windows, and interior spaces. In this video, we will explore why a veranda works so effectively, which physical processes take place beneath its roof, and how the same principles can be applied to a modern home. Let us begin with a simple observation. Imagine a shaded room and an open veranda located right beside it. The air temperature may be almost identical. Direct sunlight reaches neither space, yet the veranda almost always feels cooler. Why? The reason is not just air movement. A properly designed veranda simultaneously affects solar radiation, surface temperatures, airflow direction, and the rate at which heat accumulates inside the building. In effect, it creates an intermediate climate zone between the scorching outdoors and the interior rooms of the house. The word veranda entered European languages through Portuguese usage, but similar structures existed long before their modern name appeared. When Europeans began building houses in tropical regions, they often used the architecture they were familiar with in Europe. Thick walls, small windows, enclosed rooms, very little open space. In the cool European climate, this approach could be perfectly reasonable. But in India, the Caribbean, West Africa, and Southeast Asia, these houses quickly became overheated boxes. Solar energy accumulated in the walls and roof, while the hot air had almost nowhere to escape. Gradually, the design of the houses began to change. Buildings were raised above the ground so air could move beneath the floor. Roofs became wider. Window openings became larger. Deep shaded galleries were added along the exterior walls. Local communities had already been using many of these solutions for centuries. Their architecture was shaped not by fashion, but by a constant struggle against heat, humidity, heavy rain, and intense sunlight. The Indian verandas, the open galleries of the American South, shaded African platforms, and the wide porches of Australian homes all performed the same basic task. They prevented the building from overheating. When air conditioning became widespread in the 20th century, the need for these solutions seemed to disappear. New homes were designed around mechanical cooling. Verandas became narrower. Deep overhangs disappeared. Walls and windows were once again exposed to direct sunlight. It was assumed that air conditioning would compensate for any weaknesses in the building's design. But energy consumption increased and homes became completely dependent on electricity. Today, as cooling costs rise and summer temperatures become more extreme, architects are returning to old passive solutions, and now we can explain in detail why they work. A deep veranda cools a house through 5 main mechanisms. The first and most obvious is protecting the windows from direct sunlight. When sunlight strikes ordinary clear glass, a significant portion of the solar energy passes into the room. The floor, furniture, and walls absorb this energy and begin to heat up. They then release that heat into the surrounding air. As a result, the room temperature continues to rise even when the window itself is closed. The veranda roof intercepts the sunlight before it can reach the glass. The window remains in the shade. The interior surfaces receive less energy. This means the air conditioner, or natural ventilation, has far less heat to deal with. When the overhang has the correct depth, the difference can be very noticeable. Studies of traditional houses in Queensland, Australia, have shown that a veranda about 1.8 meters deep, when positioned correctly, can block most of the solar heat that would otherwise pass through the windows during peak summer hours. What makes this especially interesting is that the same overhang can behave differently in different seasons. In summer, the sun sits high above the horizon. The deep roof blocks its rays and keeps the windows shaded. In winter, the sun travels lower across the sky. Its rays can pass beneath the overhang, enter the windows, and help warm the room. A correctly calculated veranda therefore becomes a passive seasonal switch. In summer, it protects the house from overheating. In winter, it allows the house to benefit from solar heat. The second mechanism involves the walls. People often focus only on windows, even though a massive wall can transfer an enormous amount of heat into a house. A brick or concrete surface exposed to direct afternoon sunlight can sometimes reach 60 to 70 degrees Celsius. That heat then moves slowly through the material. Even after the sun has disappeared, the wall continues releasing the energy it stored into the interior. This is why some homes remain stuffy late into the night. The outdoor air has already become cooler, but the walls are still acting like heated radiators. When a deep veranda covers the wall, the situation changes. The surface remains shaded throughout the day and may warm only to approximately the temperature of the surrounding air. Under the same weather conditions, the difference between an exposed wall and a shaded wall can sometimes reach dozens of degrees. The less the exterior surface heats up, the less energy passes through the wall and into the building. In other words, the veranda creates a protective thermal belt around the house. It does not try to remove heat after it has already entered the room. It stops the heat outside. Preventing a building from heating up is always easier than cooling it after it has already overheated. The third mechanism is less obvious. It involves the air entering the house. The floor beneath the veranda remains shaded all day. In traditional houses, it was often raised above ground level, allowing air to move freely beneath it. This surface heats up far less than an exposed concrete path, stone patio, or dry sunlit soil. When wind moves toward the house, it first passes over the shaded zone. Before entering the windows and doors, the air comes into contact with a cooler surface rather than scorching ground. It therefore picks up less additional heat. A constant natural movement of air also develops beneath the veranda roof. As air warms, it becomes lighter and rises. It then escapes through the open edges of the structure. Cooler air from the garden or the space beneath the floor moves in from below to replace it. When the house's windows and doors open onto the veranda, this air can move into the interior rooms. The veranda therefore does more than create shade. It forms an intermediate zone through which air passes before entering the house. With good planning, this zone can improve natural ventilation and reduce the feeling of stuffiness. The fourth mechanism involves plants. Old verandas were almost always filled with climbing plants, ferns, palms, and large pots of greenery. Of course, they decorated the space, but their purpose was not limited to appearance. Plants continuously release water through the surfaces of their leaves. This process is called transpiration. Water requires energy to evaporate. Some of this energy is taken from the surrounding air and surfaces, which can slightly reduce the temperature around dense vegetation. In direct sunlight, 1 or 2 small pots will make almost no difference. But dense planting in a shaded, well-ventilated area can create a more comfortable microclimate. This effect is especially noticeable in hot, dry weather. Air passing between the leaves is partially cooled by moisture evaporation. It can then enter the house through open windows. The result is a simple living evaporative cooling system. It requires no fans, pumps, or electricity. It only needs shade, air movement, plants, and regular watering. In a very humid climate, the effect will be weaker, but shading and surface cooling will still remain useful. The fifth mechanism appears after sunset. During the night, heated surfaces gradually release the energy they accumulated during the day. They radiate heat into the surrounding environment and toward the colder night sky. On a clear night, this process is more active. Clouds, by contrast, trap part of the thermal radiation, which is why cloudy nights often feel warmer. The main problem with an exposed wall is that it can store too much energy during the day. In the evening, it begins to cool down, but at the same time, part of the heat continues moving into the house. As a result, a bedroom may remain hot until midnight or even longer. A wall shaded by a veranda heats up much less in the first place. This means that in the evening, it does not need to release a huge reserve of stored heat. It approaches the temperature of the night air more quickly and transfers less energy into the building. The house begins cooling earlier and remains comfortable for longer. This effect is easy to underestimate. A veranda does not necessarily create icy air indoors. Its main purpose is to prevent building materials from becoming solar heat batteries. That is why the result can be felt not only during the day, but also late in the evening. However, not every structure called a veranda works equally well. Its depth, orientation, height, and level of openness all matter greatly. One of the most effective designs is a veranda that extends along 3 or 4 sides of the house. This type of structure protects different walls as the sun changes position throughout the day. In the morning, it shades one side. During the day, it shades another. In the evening, it protects the facade from low western sunlight. This is why many traditional Australian houses had an almost continuous open gallery around their entire perimeter. If it is impossible to surround the whole house with a veranda, the first priority should be protecting the walls that receive the greatest amount of solar energy. For homes in the Northern Hemisphere, particular attention is usually given to the southern and western sides. The western facade is often the most problematic. After midday, the sun moves lower and shines directly onto the walls and windows. Because of the low angle, an ordinary short overhang may not be enough. A deep roof, side screens, exterior blinds, or dense vegetation can be especially useful here. In the southern hemisphere, the direction of the daytime sun will be different, so the orientation must always be chosen according to the local climate and the position of the house. Another effective design can be seen in traditional Queensland houses. The entire house, together with the veranda, was raised above the ground on supports. Originally, this helped protect the building from floods, moisture, and pests. But the design also provided additional cooling. Air could move freely beneath the floor. The ground under the building remained shaded, and wind could cool the house not only from the sides, but also from below. In hot and humid climates, this circulation significantly improved comfort inside the rooms. Modern houses often copy the appearance of old verandas without reproducing their function. For example, a very narrow canopy, less than 1.5 meters deep, may be installed in front of the facade. It may look attractive in a photograph, but on a hot summer day, it provides very little protection from low-angle sunlight, especially during the second half of the day. For a veranda to become a real part of the cooling system, its depth often needs to be approximately 1.8 to 2.4 meters. However, there is no universal measurement. The correct depth depends on the height of the wall, the size of the windows, the direction of the facade, the latitude, and the seasonal position of the sun. The depth should therefore be chosen not only for appearance, but also according to the movement of sunlight. Another common mistake is completely enclosing the veranda with glass. The open, cool zone then becomes a room that rapidly accumulates solar heat. Air movement decreases. It becomes more difficult for heated air to escape. Instead of a climate buffer in front of the house, an additional greenhouse is created. If protection from insects is needed, mesh is a better option because it barely restricts ventilation. Partial glazing can also work if it includes wide opening sections, exterior shading, and a way for hot air to escape quickly. The main principle is to preserve free airflow through the veranda. This is where the true value of traditional architectural solutions becomes clear. They rarely served only one purpose. The roof protected against rain and sunlight. The open gallery provided a place to rest while also cooling the walls. The raised floor protected against moisture and improved ventilation. Plants created shade and helped produce a more comfortable microclimate. Every detail was connected to the others. Together, they created a system that worked around the clock without a motor, compressor, or electrical grid. The veranda did not appear because someone simply wanted to add a beautiful decorative feature to a house. It was a response to a specific problem. People needed to make homes livable in climates where walls could become scorching hot in the sun and nights remain stuffy. 79 later, air conditioners allowed people to temporarily forget these principles, but the laws of physics did not disappear. The sun still heats glass and walls. Heavy materials still store heat, and shading remains one of the least expensive ways to reduce building overheating. Even when it is impossible to build a full veranda around the house, these principles can still be applied partially. Install a deep overhang above the windows. Protect the western wall with a pergola. Add exterior blinds. Create a shaded area in front of doors and windows. Plant climbing vegetation. Provide a clear path for hot air to escape beneath the roof. Each of these solutions reduces the amount of solar energy that must be removed from the house later. They also prevent the building from accumulating an enormous amount of heat during the day. All of this happens quietly, automatically, and without consuming energy. If this video has made you look at your own home differently, tell us in the comments which side of your house becomes the hottest. Do you have a veranda, canopy, or open terrace? And do the rooms behind it actually remain cooler? Like the video if you found this explanation useful, and subscribe to the channel. Here we continue exploring old and modern technologies that can cool, ventilate, and improve homes without unnecessary energy costs.